This conference will now be recorded.
Good afternoon, one and all. This is A. Rajesh from EC department. My subject is embedded system design. So after covering first unit, in second unit, we are going to study elements of embedded system. So this element of embedded system is consisting of the following topics. First, we'll cover objectives, introduction, core of the embedded system, general purpose and domain specific processors, ASICs, PLDs, commercial off the shelf components, memory, ROM, RAM, memory according to the type of interface, memory shadowing technique, memory selection for embedded systems, sensors and actuators, communication interface, onboard and external. The textbook is Introduction to Embedded System, Shibu KV. So this will cover your all 5 units. Other than that, you have reference books, Embedded System, Raj Kamal, Tata McGraw-Hill, and some other things like Embedded Design by Frank Wahid, Embedded Systems by Laila Pearson Publications, and Embedded Software Premier by David Seaman. So our required textbook is Introduction to Embedded System by Shibu KV. So objective is, after you have learned what is an embedded system and its applications and its types, classifications, now we are going to see the architecture of embedded system that will define it as elements of an embedded system. So we'll see into the embedded system by using the topic called elements of embedded system, and we are going to understand how this embedded system is going to work, and we are seeing what is the core of the embedded system and differentiate between processor and microcontroller, classify these processors based upon the architecture, and we have to compare all the processors simple to complex and the sensors, actuators and interfaces, so which together come together look like your embedded system. So in the previous chapter we have seen what is an embedded system. In this topic we are going to study about elements of embedded system and how embedded system is working. So as you know, embedded systems are nothing but the devices which are used in our day-to-day life without our knowledge, such as your refrigerator, washing machine, air conditioner, television, DVD players and music systems. So these are household appliances which are built around embedded system. All embedded systems are having hardware and software. This hardware is having the capacity to implement the specific task based upon a program given in a firmware as an application software. So this embedded system is a unique one. If you consider our vehicle automation system car, it is having its intelligence varying from headlamp controllers, engine controllers, ignition controllers to that of complex airbag control system. So a complex airbag control system is one specific task of a embedded system intelligence in your vehicle, where if any accident is occurring, the airbag automatically gets open. So this is the first embedded design implemented in our vehicle system. So like that, some other embedded designs are available. So based upon the instructions, one of the hardware gets actuated, like headlamp controllers, engine controls, ignition controllers. Among that, the first priority is airbag control system if any accident is occurring. So you can define an embedded system as having a hardware, software, nothing but combination of hardware and software, and it is an inevitable product, and it is used in all the applications fields like household appliances, telecommunications, medical equipment, industrial control, consumer electronics. So first again, once again we'll define Embedded system is an electronic electromechanical system designed to perform a specific function. So based upon the function it is designed, and it is a combination of hardware and software. For example, the hardware part, microprocessor controlling an automobile engine, is an example of an embedded system. It will run on its own, human intervention is not required, and it will respond in real time. What is real time? Like your missile system. So if you launch any missile, based on the whatever the output is there, it must be in exact, it must be real time, it is must be deterministic. So the missile should not miss the target, and it must be deterministic, or the in terms of time and in terms of location it must be specific. So that is called real time. So these are the some of examples of embedded system, like our washing machine, refrigerator, digital camera, digital watch, smartphones, medical equipment, ECG, air traffic controllers, electronic toys, automatic car, DVD players, modems. So all these all will come under applications of embedded system. So an embedded system can be thought of as a computer hardware system having software embedded in it. It can be a single system or it can be part of a big system. So what is the hardware? That hardware is a microcontroller or microprocessor, and it is doing a specific task. So what is specific means? The embedded system designed for one purpose will not be used for other purpose, such as a fire alarm in an embedded system will detect only smoke. It will not do any other task. An embedded system is a combination of three things: hardware, software, and the mechanical components, and they are doing only specific tasks. So these embedded systems are taking input as one specific quantity, and based upon that they are controlling the output quantity. So that is done by giving the signals to actuators. This actuator is going to control the output, such as your air conditioner system. If you consider the air conditioner system will just cool the room temperature. And what is the input? Input is nothing but a sensor sensing the room temperature. Another input is the temperature set by the end user. So it will compare the room temperature and the temperature required by the user. Based upon the difference, it will just run the actuator which is running the motors, so that from the outlets some cooling will come, and automatically the temperature is adjusted to the temperature set by the user. So like that, based upon an input, it is controlling another output, and input is sensed by sensors or any other images or textual way. Output is can be any of the physical quantity. So thus embedded systems can be viewed as a reactive systems. Real-time, reactive, microcontroller based systems. All may not be real-time, because like our electronic toys, we require output, but it may not be specific, it may not be deterministic. If toy is operating, it is okay. If it is delay also, we will accept. But whereas in missile system and some other industrial applications, medical applications, we will not accept any delay. So there it should be deterministic, and it should be exact in time. That is called time critical system. So time critical and real time and deterministic is coming under hard real time systems, hard real time reactive systems. If you consider some variation in its operation, so that is called a soft real time reactive systems. So what are the user interfaces are? That, like if you consider smartphone, a smartphone has an user interface from the keyboard, push button, switches, and this embedded system, based upon the input given, it will do some specific task based upon the program written in the memory. So that program is called control algorithm. So like if you consider an elevator, if two persons are simultaneously operating, based upon the program already given in the hardware, this elevator will decide to go to which position. So like that, the contents of the memory will decide what is its operation. If you consider washing machine, so washing machine, it will take the clothes and water and it will wash it for a certain time. So for that also some algorithm is written. So for each embedded system is unique, and the control algorithm is written as a software program into the hardware, and some sensors are detecting the inputs by using a push buttons or switches, and it is controlling the output. Output can be a temperature, output can be any airbag control system, like that. So an embedded system without code can be implemented based upon the requirement if it is not as real as real. So the hardware point of view, elements of embedded system, it consists of a main hardware which is controlling all the peripherals, input ports, output ports, memory, some other devices. So the main hardware, it is called system core. The system core can be a processor. This processor is connected to input ports. So it is getting its input from input ports. Input ports are generally sensors, and it is connected to memory, and memory, it is bidirectional because based upon the operations it is doing, it may require to suspend one of the operation and act to another operation. So for that, it is connected bidirectional. So contents of memory, it will get it, and this memory is holding the embedded firmware or software. So this embedded firmware software tells how a embedded system must operate. So these memory contents are bidirectional between system core and memory, and the output is connected to output ports or actuators. These actuators are connected to the outputs and some other peripheral devices. So your input ports called sensors, output ports called actuators, memory, and other interfacing devices, all are connected by some interface. That interface can be a wired one or wireless. So this interface can be an onboard or offboard. Onboard means within the PCB, all the ICs, they are communicating and exchanging the data. So that is called onboard. Offboard means this is one embedded system and this must be inserted in, it is a part of big embedded system. So and a digital camera placed at one place will capture the image and it will store in the memory, as well as it will transfer in a wireless method or wired method to some other transceiver placed at some other place. So both transceiver and digital camera will be part of embedded system. So embedded system can be a single functional, it can be a single one, or it can be part of a big system. And our system core can be an microprocessor, microcontroller, FPGA, ASIC, DSP, or system on chip. And what are the memory we are implementing? It is of two types. It is called program memory and data memory. So program memory consists of hardware applications, how a embedded system must operate. Data memory is the in-between data which is generated, like you consider the elevator. Elevator, it may be in first floor and you are getting instruction from second floor and third floor. So then the elevator will move to the third floor, then it will go to the second floor. So such type of logic is written in the embedded firmware as memory, but instructions coming from two floors and its data, it is called a data memory. So coming to core of the embedded systems, embedded systems are domain and application specific and are built around a central core. The core can be a general purpose and domain specific processor. This general purpose and domain specific processor can be a microprocessor, can be a microcontroller, can be a digital signal processor, or can be an ASIC, application specific integrated circuit, or it can be a programmable logic device, or it is commercial off the shelf component. So coming to general purpose domain specific, it is your microprocessor. The first microprocessor is Intel 4001, designed as an IC in 1971. It is having 1K data memory and 12-bit program memory, 16 4-bit general purpose registers, 46 instruction set. And from then the microprocessor era has begun, and we are having now P3, P4 processors with floating point 64-bit arithmetic logic. So like that, the embedded systems designed earlier stage are called first generation systems. Later on, it is second generation, third generation, and fourth generation. So fourth generation are your missile systems, because such applications can be implemented. First generation is the electronic toys. So like that, based upon the complexity of embedded system, they are classified into different generations, and also they are classified as small scale, medium scale, and large scale. So to design the core, we have to consider one architecture. The architecture is a Harvard architecture or von Neumann architecture. Harvard architecture means the processor is containing a separate bus between program memory and data memory. So program memory is the program written by the manufacturer, how an embedded system is going to operate. Data memory is the in-between data. So if you are using the separate bus for program memory and data memory, it is called Harvard architecture. If you are sharing the same bus using a single bus, it is called von Neumann architecture. Again, the architecture is classified into two types, RISC and CISC. RISC stands for reduced instruction set computing. CISC stands for complex instruction set computing. So general purpose processors versus application specific processor. So what is the general purpose means? Some applications like electronic toys, you can use a processor to do some task. It contains a CPU, control unit, and memory. But some applications like in air traffic control systems, missile systems, you require some specific design. So for that, you can design your own hardware processor, that is called ASIC. ASIC stands for application specific integrated circuit. Based on the application, its internal hardware is designed. So for that, you have to create your own IC from the manufacturer. So it is optimized design, optimized instruction set. It is a own processor. So like based upon the vendor, if Samsung is creating its own washing machines, it will create some separate ASICs for its all washing machines. So like that. So based upon the vendor, he can use an existing processor, or you can create his own processor. So if he is using a own processor, he has to manufacturing it from some other fab unit, that is called ASIC. So compared to microprocessors, microcontrollers are mostly used for your embedded system applications because of its inbuilt memory. So a microcontroller is a highly integrated chip containing CPU, scratchpad RAM, special and general purpose registers, flash memory, timers, dedicated input output ports, interrupt control units. So compared to a microprocessor, because this is all on board, so this microcontroller is readily available and cost effective. So various vendors are available like Philips, Atmel, Maxim, Microchip, but the dominant microprocessor is Intel 8051 microcontroller and Automotive AVR. So we'll differentiate what is a microprocessor and microcontroller. Your microprocessor is nothing but central processing unit capable of performing arithmetic logic functions. So it will do all arithmetic and logical functions. whereas microcontroller is containing a CPU scratch pad, special and general purpose register arrays, ROM, flash memory for program storage, timer, interrupt control unit, dedicated I/O ports. Microprocessor is dependent unit, whereas microcontroller is a self-contained unit. On board, it is having timers, interrupt controllers. Microprocessor is a general purpose, whereas microcontroller is application oriented, and the time to market is important for both selection of microprocessor and microcontroller. Microprocessor will target all high-end market designs where performance is important, where performance is not so time critical. You can use a microcontroller. Power saving techniques are used in microprocessor and microcontroller, but among that, microcontroller is having lots of power saving features. So the hardware is called system core. The system core, first one, it is a general purpose. Under that, you can use microprocessor or microcontroller or a DSP. DSP stands for digital signal processor. It means all computational and power constraints. It is faster, 2 to 3 times faster than your microprocessor microcontroller. It is having program memory, data memory, computational engine, and input output units. So like your TMS processor. So these three are general purpose. They can be RISC or CISC. So what is RISC means? They are following reduced instruction set. So number of instructions used are less in a RISC, whereas in CISC there are more number of instructions. In RISC we are following instruction pipelining. So by using instruction pipelining, you are increasing the computation speed. So what is instruction pipelining is, if a microprocessor is doing some instruction execution, first it is going to fetch it from the memory. So it is fetching, it is executing it. So at that time it can simultaneously call another instruction. So instead of wasting CPU time, if like now the present processors are dual core, multi-core, quad core, so simultaneously you can do two operations. One instruction it is fetched, another instruction is in the execution stage. Or if you go for CISC architecture, there is no instruction pipelining. So one instruction is totally executed, then only we'll go to the next instruction. So such a design is called CISC architecture. So there are more number of instructions and no instruction pipelining. Whereas RISC architecture, you are having less number of instructions and we are following instruction pipelining. And orthogonal instruction set is available here for all the registers. Whereas CISC architecture, there is no orthogonal instruction set. RISC architecture is having large number of registers, whereas CISC architecture is having less number of registers. Because we are following instruction pipelining in RISC architecture, we have to save the contents of one instruction while you are executing or fetching another instruction. So you require more number of registers. And the programmer needs to write more code for this RISC architecture, whereas the programmer needs less code to be written for CISC architecture. The instruction set is fixed here in RISC, whereas it is variable in CISC. And RISC architecture is following Harvard architecture. Harvard means you are using a separate bus for memory, program memory and data memory. Whereas CISC architecture, we can use Harvard or von Neumann. It is depending on, say, processor, DSP, microcontroller, microprocessor. If it is having a CISC architecture, it can follow Harvard architecture or von Neumann architecture. So what is Harvard architecture and von Neumann architecture? Harvard architecture means we are using a separate bus for instruction and data fetching. Von Neumann architecture means we are using a single bus for instruction and data fetching. So once you want to execute an instruction, you are going to fetch the instruction, then you are going to fetch the data. So if these are done by a single bus, it is called von Neumann architecture. If you are using a separate bus it is called Harvard architecture. So because you are using a separate bus, we follow pipelining and performance speed is increasing. Whereas Von Neumann architecture, low performance compared to Harvard architecture. Harvard architecture is comparatively high cost. Von Neumann architecture is cheaper. No memory element problem in Harvard architecture because both memories are separate and separate data buses are provided. So there is no memory alignment. But because we are using a shared bus, memory alignment may occur and some of the data may be corrupted or accidentally it can be leading to corruption. Whereas there is no corruption, data is secure in Harvard architecture. So this is a diagram which is showing where input output CPU and memory are connected by a single bus, that is shared bus by called Von Neumann architecture. Whereas Harvard architecture, if you see, program, CPU, data memory, all are connected by a single bus. So again, your processors, they are defined in terms of architecture or in terms of instruction set, or they are defined in terms of Indianness. What is this Indianness is how memory contents are stored into the memory, because if you are fetching an instruction, it has a higher byte and lower byte. So based upon the contents saved in the memory, they are classified as Indianness. If higher order byte of your data is stored in a memory at a lower address and lower order byte is saved at a higher address, it is called big Indian. If lower order byte is stored in memory at lower address and higher order is stored at higher address, it is called little Indian. So processors are also classified based upon Indianness. Big Indianness is easier to determine, easier to compare numbers, easier to divide numbers. Whereas little Indian means it is easier only for addition and subtraction of multi-precision numbers. So the first one is general purpose processor for a system core of your embedded system. And the second one is application specific. So as I told, application specific is a application specific integrated circuit designed by a vendor. So this ASIC is a microchip designed to perform a specific and unique application. It integrates several functions. So the hardware part, the instruction set, the memory, everything is related to the manufacturer vendor. So you can consume less area, high speed, memory control, everything, memory control, power control, everything is decided. Whereas if you consider general purpose processors as your system cores, area you have to compromise, power you have to compromise. So depending upon the requirement, if you are using ASICs, they can be implemented by a gate array architecture, standard cell architecture, or full custom designing. Full custom means the entire design we are going to design by one program. We are going to get a gate level netlist. From the gate level netlist, we are going to design a layout, and that layout is sent to the fab unit. This fab unit persons are going to create an IC. So your hard system core can be a ASIC. If it is an ASIC, you can follow a gate array architecture, you can follow a standard cell architecture, or it can follow a full custom designing. Customizing means logic as well as routing is designed by the manufacturer. So this is the layout of a ASIC, mixed signal ASIC, where internal to the design there is an analog portion, there is a digital portion. These boundaries are your input output circuits. This is an EEPROM. So together it looks like this. The internal hardware is, in terms of layout, this ASIC looks like this. So system core can be a general purpose. General purpose can be a microprocessor, microcontroller, or DSP, or system core can be an ASIC. And next, the system core is your PLD. So programmable logic devices. These are semi-custom devices. Only you have to program it. Hardware it is available. Hardware it is available in terms of an and OR array. So there is some specific set of AND gates, specific set of OR gates, only you have to just program this AND plane and OR plane. So PLDs are the ICs which contain an array of AND gates and another array of OR gates. They are having programmable features. This programmable feature classifies them into three types: programmable read-only memory, programmable array logic, programmable logic array. So the process of entering the information into these devices is known as programming. This can be done by electrically method. So for this you need a Boolean function for the specific logic. It is hardware programming, not software programming. So we are creating our own hardware system core by programming. So this PLD, programmable logic device, is of two types: CPLD. The smaller classification is ROM, PLA, PAL. So a PLD can be one of these things. It can be a ROM, it can be a PLA, programmable logic array, or it can be a programmable array logic. But combining this PLDs, we can create big architecture. That is your CPLD. This is your CPLD, complex programmable logic device. This CPLD has some logic up to 1000 gates, whereas FPGA is a field programmable gate array where performance and high density logic is used, and it is programmed wherever required based upon it is kept in a socket, and the user can directly program this FPGA. The advantage of PLDs are they offer customer much more flexibility during design cycle. They do not require long lead times for prototypes or production parts because PLDs are already on distributor shelf ready for shipment. So PLD is available ready-madely. You can just only program it. So your hardware can be a PLD. PLD again is classified into ROM, PLA, and PAL. PLDs can be reprogrammed in some designs, even if it is shipped to a customer. So the structure of PLD consists of you are having PLDs connected by interconnection logic, and these are connected together by input output blocks. So if you see the structure of CPLD, it is having PLDs connected by bidirectional buses using interconnection wires, and they are surrounded by input output blocks. So PLD is simple PLD, CPLD means complex PLD. But if you go to FPGA, this architecture is entirely different. The FPGA architecture is you are having configurable logic blocks connected by switch matrices, and they are covered by input output blocks. So surrounding to the external pins, we are having input output blocks. This input output block is programmed to act your input as input or output as output, or there can be anything. Your pins can act as input output, but internal logic is CLB, configurable logic block, which is nothing but a lookup table. So based upon the program written, you have to configure your FPGA by using a program. So your program, whatever the program written to implement any hardware, that hardware program is dumped into an FPGA into a CLBs connected by switch matrices. So coming to ROM, ROM is a memory which stores information permanently. So that's why it is called read-only memory. So because your embedded system is a ready-made device used by the end user, so this programming is done by the manufacturer. So a manufacturer is going to program its logic into the hardware that is called system core. So that is your programmable ROM. So the binary information, whatever it is programmed, now we have a capacity that we can also electrically program this ROM, and that's why it is called programmable ROM. It is programmable ROM because the manufacturer can program the binary information electrically once by a PROM programmer. It is consisting of a fixed AND array and programmable OR array. This AND plane is going to implement product terms. Product term is nothing but a min term, and the OR plane is going to implement sum of some terms. So like that, we are implementing sum of min terms in a read-only memory. Whereas if you consider programmable array logic is a programmable logic device, whereas you are having a programmable AND plane and fixed OR array. So PAL is having a programmable AND array and fixed OR array. So the advantage is we can generate required product term in terms of Boolean function instead of generating all the min terms by using programmable AND gates. Again, AND plane is going to generate product terms. OR gates are going to generate some terms, but here they are not programmable. So the number of inputs to each OR gate is fixed. Only you have to program the AND array and generate the product terms. Programmable logic array is another classification where you are having both programmable AND plane and programmable OR plane. So both are programmable. AND array is programmable and OR array is programmable. So when we are coming to comparison of CPLD, FPGA and microcontroller, FPGAs are more flexible compared to CPLD and microcontroller. FPGA is internally storing the data in terms of lookup table. Lookup table is nothing but a memory where you are storing the contents of any logic in the memory, and inputs are acting as its address lines. Complexity wise, if you see, FPGA is more complex compared to CPLD and microcontroller. It is not a computing system, it is just a hardware consisting of all the gates, lookup tables. It is a complex hardware compared to CPLD and PLDs. So depending on the application, an FPGA can be used instead of going for an ASIC. And processing speed is also faster in FPGAs compared to CPLD and microcontroller. So as we told, your embedded system is having nothing but a sensors, actuators, memory, system core, and some other peripheral devices. So the system core is nothing but general purpose processor, which can be a microprocessor, microcontroller, and DSP. So your system core can be a general purpose like microprocessor, microcontroller, and DSP. Second one, it can be an ASIC, application specific integrated circuit. Third one, it is a PLD, programmable logic device. This PLD can be again CPLD or FPGA. And the fourth one is commercial off-the-shelf component. So what is this commercial off-the-shelf product is? It is ready-made. It can be used as it is. Okay. So you are designing an embedded system. You are connecting sensors, hardwares, peripherals, actuators. You can directly use the main hardware core as is ready-made PCB. It is used as it is available. It is designed around a general purpose or domain specific or ASIC or PLD. So the manufacturer has designed its logic in terms of any of its hardwares. Advantages of COT is it is readily available in the market. You can directly insert in your embedded system and utilize it. It acts as a system core. The major drawback of using COTS in embedded system is if manufacturer withdraws the product, you cannot utilize the device once again. As technology is changing, if manufacturer is not rebuilding it. So the example is electronic toy. This electronic toy is consisting of a COTS hardware unit called remote controlled toy car control unit. So what is this remote controlled toy car control unit is? This control unit is having an RF circuitry, high performance, high frequency microwave electronics, high bandwidth analog to digital controllers, converters, devices, components to operate at high temperatures, optic infrared imaging arrays, UV and IR detectors. So depending upon this remote control, this single PCB RF circuitry is nothing but the control unit, which is controlling the sensors as well as output devices. But internally, this is built by the manufacturer as a RF circuit consisting of so many components. So another example is TCP/IP plugin. So this TCP/IP plugin you can directly insert to your personal computer. I can utilize this. This is also one of the example for COTS. What are the advantages of COTS? COTS is ready to use, easy to integrate. It is reducing the development time. So what is the drawback? If manufacturer is withdrawing its development, the further you cannot utilize the device, and you have to follow common standards. So whatever the standard manufacturing standard he has prescribed, that you have to use it. But if you are having own processor, you can use your logic. Coming to the next hardware part. So embedded system, major part is system core. That is it's the brain of your embedded system. That is called system core. That is your processor. So we have discussed 4 types. One is general purpose, another is ASIC, next is PLD, next is commercial of the shelf component. Next, coming to memory. What is memory? Memory is a physical device where you store some programs. It can be a program memory or a data memory, temporarily or permanently. So depending upon the memory, you can store the contents temporarily or permanently. So this is an Arduino board connected to a memory. So memory is becoming the important part of your embedded system, because this memory is going to store the contents of your software or firmware. And this memory can be a program storage memory or a data memory. If all program memory and data memory is part of your embedded system, that memory is called on-chip memory. If they do not contain sufficient memory and you are connecting an external memory, it is called off-chip memory. So your embedded system components, peripherals can be on a single board, or they can be a part of separate boards, and they are together connected in your system. So in such a case, such type of memory is called off-chip or external memory. Depending on the memory modules required by the system, your memory selection is done, and that is specific to the microcontroller based. So based upon the microcontroller, your memory is selected. Memory is major classification is it is volatile memory and non-volatile memory. So first, coming to volatile memory. Volatile memory means it will hold the contents till power is applied to them. So that's why whatever the system memory we are selecting, like program memory, that is holding the software or firmware contents in a ROM, read-only memory. So how ROM is created? ROM is created as logic of ones and zeros stored in its memory by using some electrical pulses or fuses, which are permanently burned, so that your data is designed by the manufacturer. Again, you can't edit it. That's why it is called read-only memory. So RAM means random access memory. You can read and write. So your data memory, mostly it comes under RAM. It is volatile. It will hold the contents as long as power is applied to them. Once power is switched off, they lose the contents. So such as information related to day-to-day applications of your embedded system utilization, those data will be lost, but data related to your functioning of your embedded system will be stored in ROM, read-only memory, and that is done by the manufacturer. So coming to volatile memory, RAM, they are of 2 types, SRAM and DRAM. SRAM stands for static random access memory. It retains the data in its memory as long as power is supplied. SRAM do not require to be refreshed periodically. So this RAM read-write memory, again it is of three types: SRAM, DRAM, which are coming under volatile. Other than that, you are having one more type of RAM called non-volatile RAM. So what is SRAM? SRAM stands for static RAM. It provides faster data access compared to your DRAM. It stores the data as 4 transistors connected as cross coupled, like your two inverters. Two inverters are cross coupled, and it stores the data at the output portion of one inverter. So these 4 transistors are connected as cross coupled inverters, and after that you are having two more transistors which are connected to your bit and bit lines, and the gates are connected to the word lines. So while operating this, you can operate them as read operation or write operation. So if you want to do write operation, you have to write the contents on the bit lines: bit line normal B, bit line B bar. So data and its complementary data both will be written in the memory. So word line will be given logic 1, means its gates are connected to logic 1. So in the diagram, if you are seeing, if gates are connected to logic 1, this MOSFET is going to be switch on. Once it is switch on, the contents of bit lines are stored in the output of your CMOS inverters, and the CMOS inverter is cross coupled. This output is converted to gates of another inverter. The right side output is connected to gate of left side inverters. So like that, this data is rotated in between these 4 transistors, and it is always retain the value. But if you want to read the data, just the data written in the contents of outputs of your CMOS inverters will be read by applying word line as 1. So those data will be given to bit lines. So this is only 1-bit memory implemented SRAM cell. SRAM is having large storage capacity for on-chip. It can be used in smaller and large capacities. It is having low latency and high performance. Latency means the delay between input to the output. So SRAM is been be designed very easily compared to other memories. Applications, it is used as a faster buffer for medium size block of data. It fits for on-chip memory having lower latency. If your memory is ranging more than 10 MB, you can consider such types of SRAMs. So under volatile, it is static RAM. So next it is dynamic RAM. Dynamic random access memory stores each type of data on a capacitor within a separate capacitor. So here there is a MOSFET. At the gate side, we are connecting to the word line. At the drain side, we are connecting to the bit line. At the source side, we are connecting a capacitor. On the capacitor, within the capacitor, we are having this data stored. So this is one efficient way to store the data. And compared to your SRAMs, these DRAMs are occupying less area. They hold more amounts of data, but require to be constantly recharged to keep the charge. So that's why this DRAM is requiring more power. You have to refresh periodically. So this is the DRAM cell 1-bit implementation. Word line data is, if it is logic 1, this bit data is stored on the positive terminal of your capacitor. If word line is 0, okay, this data will retain. Once you give, that is for write operation. If you want to do read operation, already data is in the on the positive plate of your capacitor. Was just give word line 1, this MOSFET will become on, and this bit line is going to get the data from the positive terminal of your capacitor. Means it is going to discharge whatever the value is on the capacitor, that is going to discharge to the bit line. So this DRAM memory chip is consisting of storage locations or memory cells. It is consisting of a transistor and capacitor which can hold the data in active or inactive stage. So what is this active stage? Is this holds the value at active 1 once you charge it to high state. And deactive means it can store the value 0 once it is in below level. It is not charged. So the storage capacity is very high, low cost device. It is also used for storing large blocks of data, and it is used in executing microprocessor code. So whatever the microprocessor instruction is there, that is can be stored in this such type of memory while executing. So those instructions you can store here. Low latency. So your ROM, read-only memory, is non-volatile. This is having various types of classifications. First one is programmable ROM. So programmable ROM means one time you can modify, that is done by the end user. So actually PROM is designed with fuses by the manufacturer, but this fuses again you can how these fuses are done is the chip is programmed by the PROM programmer, wherein some fuses are burnt. The on fuses are read as zeros, while the burnt fuses are read as zeros. On fuses are read as ones. So once I'll tell, read-only memory is a non-volatile memory. This read-only memory is having various classifications. First is programmable read-only memory, that stands for PROM. Programmable read-only memory, it can be modified only once by the user. It is manufactured with a series of fuses by the manufacturer by using a PROM programmer, where some fuses are burnt. The on fuses are read as zeros. Sorry, the on fuses are read as ones, while the burnt fuses are read as zeros. So this is code memory. So what we call as program memory or code memory, consisting of the software part, is stored in ROM. It is of various types: PROM, programmable ROM; EPROM, erasable programmable ROM; EEPROM, electrical erasable PROM; flash memory. And your code memory can be non-volatile RAM. So after PROM, programmable ROM, we are having electrical erasable programmable ROM, EPROM. EPROM stands for erasable programmable ROM. Here it is not electrical, it is done by an UV light, ultraviolet light. So the write and read operations can be performed on this EPROM. The ultraviolet light will erase its contents, making it possible to program the memory. Next is electrically erasable PROM. Electrical erasable PROM is a modified read-only memory where data contents can be erased any number of times by using electrical erasable method. So these contents are erased by exposing it to an electrical charge. The EEPROM stands for electrically erasable programmable read-only memory, is stored and removed 1 byte of data at a time, does not require to be removed from the computer. The charging of the content does not require additional equipment. Any number of times you can do the write operation, it will operate. The common cell structure consists of 2 transistors and a floating gate architecture. And again, subclassification of EEPROM is serial EEPROM and parallel EEPROM. Parallel EEPROM is faster, cost effective compared to serial EEPROM. Flash memory. Flash memory keeps, it is widely used among your electronics and computer devices. And this is a special type of memory where data can be erased and programmed with a block of data. It keeps the data even there is no power. It works efficiently than compared to EEPROM. Is designed for 1 lakh to 10 lakhs of write cycles. It requires number of data to be written is less. The main content with flash ROM is number of times the data can be written. The data can be read from the flash memory as as many times, and as many times you can do the write operation. Next is memory shadowing. So if you see the embedded system, we are having sensors, actuators, peripheral devices, memory connected to your system core. System core is the hardware. So hardware can be general purpose ASICs, PLD, or commercial off-the-shelf components. Coming to memory, there is a code memory called program memory. There is a data memory. So generally code memory or data code memory or program memory is a ROM. Again, ROM is subclassified into PROM, EEPROM, EEPROM, flash memory. And whereas data memory, it is a RAM. It is again classified as SRAM and DRAM. So what is this memory shadowing is? Memory shadowing is a method used to keep track of memory utilized during the execution of program in your computer. So if you want to utilize memory, you can do segmentations. So if you want to use efficiently, you are having only 64 KB of memory, but you want to use memory as 1 GB by using segmentation. So virtual address techniques you can use. So in such a case, you can keep track of the memory utilized. I can use those portions of memory which are not frequently required. So shadow memory consists of some shadow bytes that will help you to guide through these singular bits. The technique is utilized by memory error check method, where it can store information on part of the memory where it is allocated to the program being checked. This shadow memory is then used for detecting and reporting incorrect access of memory, even though the program may not be crashing out due to segmentation. So the error checker can be a memcheck. It is a part of Valgrid suite, or it can be a thread sanitizer or data race detector. So these two error checking methods can be used to create shadow bits, and these shadow bits are used to assign the memories. Memory selection. So how you select a memory, that is totally dependent on microcontroller based, but still some parameters are considered, such as speed, data storage, size and capacity, bus width, latency, power consumption, cost. So coming to sensors and actuators. So your embedded system is having its input side a sensor, its output side an actuator. A sensor is used for taking input, and it is a transducer. It will convert energy from one form to another form. If you consider the temperature sensor, it will detect the temperature as its input, and output it will generate an electrical signal to be given to an A to D converter. This A to D converter will convert the electrical pulses into a digital one. This digital pulses will be stored in the memory, and your processor, the hardware system core, will going to process this data. Then it is converted to again an analog signal. This analog signal is given to an output, that is your actuator. So here sensor is used for taking the input, whereas actuator is used for output. Actuator is also a transducer where electrical or mechanical signals will be converted to physical actions. So physical actions means it can be like your LED. If you consider LED, based upon the electrical signal generated, it will give the output as LED. Diagram, we are just seeing a soil sensor where the two anode and cathode will be are connected to one Arduino board, and this sensor is going to tell soil moisture content. So based upon that, it will invoke one of the devices connected to your embedded system. In some application, this sensor will also prompt some buzzer, or it will provide some LCD displays. So you are having infrared obstacle avoidance sensor, you are having ultrasonic sensors. So these all are sensors input to your embedded systems, whereas this slide is showing actuators, a webcam, output, microphone, printers, speakers, monitor, printer, headphone. So this is an Arduino board consisting of LEDs, relays, LDR light sensor, temperature sensor, infrared sensor, buzzer, output device, buzzer, potentiometer, push buttons. So this Arduino board is having all sensors and actuators. So with this, we'll stop this video. We'll cover our next topic in another video. Communication interfaces.